Today we'll look at limits and continuity. We've seen limits already. If you recall, we were finding f-x with first principles by doing the limit as h approaches 0, f of x plus h, take away f of x over h. So what we were doing is limiting that h value, getting it to tend towards 0. So it's a similar idea for this particular section of the course. So we're going to say that limits exist from the left and the right. I'll go on to explain that. If the value of f of x approaches a number p as x approaches a from the right hand side, then this is how we write it. So this means that what I'm going to do is approach this value a. So when x approaches this value here a, this plus means from the right. So swing in from the right hand side. So I'd be coming in from this direction here. And when I approach that particular value from the right hand side for the function f of x, then the value is p, whatever p is. And vice versa, I can control the direction of the approach by changing this a to a negative. That means approach from the left. That means to approach from the left hand side coming into a particular value. The limit as x approaches a exists only if both the limit from the left and the limit from the right exist and are equal. So the limit from the right and the limit from the left have to be there, okay? So those two are important, and they've got to be the same for us to say the limit exists. Right, so consider the following hybrid function. What they want us to do on it is work out what the limit as x approaches 1 from the right hand side for the function is. So we're going to say that the limit as x approaches 1 from the right for f of x is equal to, right, so here's x is equal to 1. This line here is x is equal to 1. Right, and what we want to do is approach that value there from the right hand side. So we're swinging in from this direction here. Okay, now where is the function defined? Well, here it is. So here's the function here. So as I approach from the right hand side to x is equal to 1, what I note is that the y value produced is going to be equal to 6. Okay, so like a 2, then it's 6, 1.5, it's 6, 1.1, it's 6, extremely close to 1 is equal to 6. Now notice here that the dot is actually at 5 at x is equal to 1, but I'm not actually at x is equal to 1, I'm approaching 1. Okay, so I'm getting infinitely close to 1. At x equals 1, the value is 5. And then let's approach from the left-hand side. So the limit as x approaches 1 from the left-hand side for the function f of x is equal to. So what I'm doing is that I'm approaching from this direction, from the left-hand side. So I'm coming in from the left. And what I can see is that these are the y values. So it's like 0, 0.1, 0.2, 0.3, all the way up to what I'm presuming is a value of 1. Okay, so it gets infinitely close to the value or the y value 1, but it doesn't actually get to 1 itself, okay, because 1 is hollowed out. There the value is 5. Okay, does the limit exist? No, as the limit as x approaches 1 from the right for the function is not equal to the limit as x approaches 1 from the left for the function. Right, that's why the limit doesn't exist. Okay, the limit from the left and the limit from the right are not the same value. Okay, and so we say here that the limit does not exist. There is the famous clip. The movie's probably getting a little bit old and dated now. I'm not sure whether you've seen Mean Girls, but there's this famous clip at the end where Katie squares off against the resident math nerd from the other school and gets this particular question here. So she wanted to evaluate the limit as x approaches 0 for this particular function here. Okay, so pretty nasty looking function. So what she does is she thinks about it, and in her mind she's thinking about the hot guy in the movie, but over in her peripheral vision she sees the teacher explaining what I've just explained here, which is for the limit to exist, the limit from the left and the right has to be the same value. So let's do this and see why she gets the answer correct, which is she says the limit does not exist. That's the answer. Everyone applauds. She gets the hot guy, etc., etc. So limit as x approaches 0. So we're going to test whether the limit exists. Here's the graph of the function. I graphed this myself just to sort of see whether the movie was correct. So the limit as x approaches 0 from the left-hand side. So here we are, we're approaching x is equal to 0 from this side here, and we can see that the y values approach infinity. Let's call this a function, so approaches infinity. Over here, the limit as, scroll down a bit, the limit as x approaches 0 from the right-hand side for the function is, well, there isn't any values over here. It doesn't exist, okay? So this does not make sense. And we note that these two values don't match up. For it to exist, the limit would have to be positive infinity as well from the right-hand side, and then this would be able to be evaluated, but it couldn't be evaluated. She says the famous words, the limit does not exist, and then everyone applauds, yay. Right, so check out the movie, it's a good one if you haven't seen it. Right, so on to the limit existing. So we're going to focus now on continuity. All right, so limits help us understand whether the function is continuous at a point. Right, so a function f is continuous at a point x equals a if the following conditions are met. The function is defined. Okay, so there has to be a value at the point. All right. Otherwise, if it's not, there's no value there, then the function is not there, which means it's not continuous at that point. All right. Now, the second one, or the second condition has to be met, is that the limit as x approaches a for the function has to be the same as the value that the function is defined as at the point. Okay. So this is the limit test to see whether the limit exists. Okay. So that's important. The second one that we do with this is we make sure that when the limit exists, the limiting value will be the same as f of a, that is, same as the value at that point. Now, this may not make a lot of sense as I'm talking about it now, but hopefully it does once I go through a few examples. So the first is easy to test. What we do is we just go, oi, are you there? So does the point exist? The second is a little bit more tricky. What we do is we consider the left and right limits, approach from the left and right, and make sure we get the same number. If we don't get the same number, then we've got a discontinuity. If we do get the same number, then that number has to match the value of the function at that point. Okay. So what we're going to do is work it through for a couple of examples. State the values for x for which the functions below have a discontinuity and give reasons. So it's clear for this one here that there is a discontinuity at this point here. All right, so let's find out why there is a discontinuity. So what we're going to do first of all is test whether the function is there at x equals 1. So let's say that this function is f of x. We're going to call it f of x. Okay. So the first thing we're going to do is we're going to find out what f of 1 is. F of 1 is equal to 3. Okay, equal to 3. Therefore, f of x defined at x equals 1. That's a good sign. Okay, for the function to be continuous, it has to be defined. By the way, I know that there's a discontinuity here. I know that this isn't a continuous function, but I need to give reasons why. Okay. All right, so now what we're going to do is test the limit for the function at the point x is equal to 1, because this is where the discontinuity is. All right, so what I'm going to do is say that the limit as x approaches 1 from the, I don't know, let's swing in from the left first of all, so the function is equal to, so I'm coming in from the left-hand side, and what I can see is I'm approaching the value 2. Okay, that's where my y values are getting closer and closer to. I'm going to say that the limit is 2. The limit as x approaches 1 from the right for the function, so let's swing in from the right now, and I can see that it approaches the same value. Now that's a good sign. It says that the limit exists, okay? But because the limit as I approach from the left and right is 2, which is not the same as the value of the function at that point, I can conclude that the function is discontinuous at x is equal to 1. So I'm going to say here that f of 1 is not the same as the limit as x approaches 1. And when I say x approaches 1, it implies from the left and right. Therefore, so because those values don't match up, I'm going to say that the limit, that therefore f of x is discontinuous at x equals 1. All right. Now remember, the way to think about continuity as well is to think about whether you can draw the function without lifting your pen up. That's a really loose way of describing continuity. So if I was to draw this function, I'll draw a line here, lift my pen up off the paper, draw the dot, and then continue it along. I can't draw this function in one continuous line, so therefore it's not continuous. But again, if you've been asked, state the reasons why or give reasons, you're not allowed to say in mathematics, because I can't draw it without lifting my pen up. It has to be mathematical reasoning. All right, so let's do part B now. And what I can see is that there's clearly two discontinuities. There's one here, because if I had to draw it, I draw that part, lift the pen up, then draw that part, lift the pen up, and then draw that part. Okay, so there's two discontinuities. There's one at x equals 1, there's one at x equals negative 1. All right, so what we're going to do for this one here is we're going to choose one of them. Okay, we're going to choose one of the discontinuities. Let's choose x is equal to negative 1 because we did one for this one. Okay, so the first thing is we do an are you there check. Okay, so we're going to do an f of negative 1 equals, looks to be 2. So that's a good sign for continuity, is that the point has to be there. If the point's not there, then give up. It's not continuous there, and you don't even need to check the limits. So f negative 1 equals 2, therefore f of x is defined at x equals negative 1. So that's a good sign for continuity. That's what I need to happen first. All right, now let's do a limit check. Right, so what we'll do is we'll go limit as x approaches negative 1 from the left-hand side. So let's swing in from the left and note that the value produced by the function is, it looks to be up to and getting closer and closer to 2. Okay, now let's swing in from the right. So approach negative 1 from the right-hand side for the function. So as I approach from the right-hand side, I can see that these values, I'm presuming they're going, yeah, it's asymptotic, so it's going to approach positive infinity, so a negative infinity rather. Okay, so we're noting here that the limit from the left and the right are not the same. Okay, so we're going to conclude here by saying it's discontinuous because the limit does not exist. So the way we're going to write that down is as follows. So this is our conclusion here. The limit as x approaches negative 1 from the left for the function is not equal to the limit as x approaches negative 1 from the right of the function. Therefore, the limit does not exist, and thus f of x is discontinuous or not continuous, continuous at x equal negative 1. All right, again for this one here we can see very blatantly that this is not a continuous function, because if I was to draw it, lift up pen, then draw that part here. So we're testing this point here, or showing via calculations that there is a discontinuity here. So what we'll do first of all is an are you there check. F of 1 equals 1. Therefore, f of x is defined at x equal 1. All right, so that's a good sign for continuity. It's got to be defined. Now what we're going to do is a limit check. This will be exactly the same as the previous one that we did. X approaches 1. Let's swing in from the right-hand side this time. So as I approach from the right-hand side, I'm approaching the value 2. Let's approach from the left-hand side. And that is going to be 1. All right, so what's our conclusion? Well, because the limits aren't the same, we say that the limit doesn't exist, and thus the function is discontinuous at x is equal to 1. So let's say that in conclusion, the limit as x approaches 1 from the left is not the same as the limit as x approaches 1 from the left for the function. So therefore the limit does not exist, and thus f of x is discontinuous at x equal 1. Okay, for each function, state the values of x for which there is a discontinuity and use the definition of continuity in terms of this to explain why. All right, so what we'll do for each of these is see whether there is a discontinuity. So for the first one here, let's quickly graph it. So I've got 2x where x is greater than 0. So sub in 0, which is 0. So that's going to be included, and it's going to look like that. So this is going to be a rough sketch. Right? Now what we're going to do is sketch this function here for less than 0. So I'm going to put 0 in itself. That's going to be 1, not included, and it's got a negative gradient, so it's going to look like this. All right, so clearly this one has a discontinuity in it. Okay, so A is a discontinuous function. I'll do B next and work out whether that is a discontinuous function or not, and C, and then we'll go from there. So here's C. So it's x, the values of x less than or equal to -1. So let's pop -1 in there, which is -1. So when x is -1, y is -1. And that point is it included? Yes, it is. And what's the gradient? It is positive. It's going to go like that. Between -1 and 0. Ooh, see, I shouldn't have. I jumped the gun there. So -1 to 0 is x squared. All right, so it's going to go like this. All right, so now we're going to do x squared. So I bang -1 into it, which is 1. So when x is -1, y is 1. All the way to 0 when I put 0 in, so that is that. I think I shouldn't have hollowed that out. It should be like that. And it's hollow there. All right, and then -2x plus 1, so that is that included. Y-intercept of 1, negative gradient, which means it goes like that from there. So I can clearly see I've got 2 discontinuities there. Okay, so that one there is worth checking up on as well. Now this final one, we've got x greater than or equal to 0. That's that. -2x for less than 0, which is something like that. So that one there is a continuous function, so I don't need to worry about that one. In fact, let's do it anyway. So what I will do is do it, and I'll say show that f of x is continuous for all x. All right, so what I'll do, I won't work this problem here because it's going to take a lot of work, and the example from this point on is fairly similar to the previous ones. I will work this one and I will work this one. All right, so the first thing I'm going to do is talk in A, I'm going to talk about why it is discontinuous. So this is my evidence. So first of all, I'm going to check or do an are you there check. So the point in contention is 0. So f of 0 equals 0. Therefore, f of x defined at x equals 0. So that's a good sign. All right. Then I'm going to do the limit as x approaches 0 from the left for the function, which is, as I approach from the left, that's going to be approaching 1. The limit as I approach 0 from the right-hand side for the function is equal to, so I'm approaching from the right-hand side, and I can see I'm approaching the value 0. So what I can quickly see here is that the limit from the left and the limit of from the right don't match up. So I'm going to say that, in conclusion, the limit from the left, the function, is not the same as the limit as x approaches 0 from the right for the function. Therefore, limit does not exist at x equals 0, and thus, so because the limit doesn't exist, thus the function is not continuous or has a discontinuity. All right, now let's do E. So what I'm going to do is show that f of x is continuous for all x. All right, so what will happen for this one here is that I'm going to do f of 0, then I'm going to get the limit from the left, the limit from the right, and all of them are going to match up perfectly, and noting that it is a show that question. So I'm going to do f of 0 equals. Now it's important for show that's to show which one you're actually putting it into. So that's this one here. So I'm going to say f of 0 equals 0. Now if it was this one that you're putting into, you would need to put a calculation in like -2 times 0 to show that, okay, to show some working. So therefore f of x defined at x equals 0, which is a good sign for continuity. Now let's check the left limit. So x approaches 0 from the left. The function is, okay, and again, if this is a show that question, I need to show what I'm doing. So when I'm approaching from the left, that'll be 0. The limit as x approaches 0 from the right of the function is equal to, so what it's going to do is I'm going to put 0 in there, equal to -2 times 0, which is 0 again. All right, again, notice what I'm doing is showing that I'm using the value. All right, so what I can conclude here is that the limit as x approaches 0 from both the left and the right, the function, is equal to f of 0 itself. They both come up as 0 and 0. Therefore, f of x is continuous for all x. All right, so there is your work, 17F, questions 1 to 4. There'll be a worksheet also following up on some of these ideas.